The set of tangent measures at a point are invariant under a couple of simple operations, and it will be helpful for us to understand the properties of any family of measures with the same invariance properties. And these families will be called cones. So suppose we have a radial measure mu and a point A and its support, where the tangent measures are non-empty, and suppose nu is a tangent measure given as the following limit of blowups, using some coefficients c sub I and some radii r sub I converging to 0. Then it's not hard to show that any multiple of nu by a positive number c is also a tangent measure. So this is because we can express c times nu as c times the weak limit of these blowups, but then we can pull the constant c inside this limit. And then we again have a sequence of constants times a sequence of blowups of mu. And by the definition of tangent measures, such a limit must also be a tangent measure of mu at A. Tangent measures are also invariant under dilations at the origin. By dilation at the origin, we mean scaling the support of the measure nu, or equivalently, a push forward of nu under the map T0R. So this will be the measure defined by, so the push forward of nu under T0R of a set A is equal to nu of R times A. Now, it can be shown that this measure, so T0R push forward nu, is equal to the weak limit of the push forwards of the sequence of measures converging to nu. And furthermore, we can pull the constant ci outside this push forward operation, so outside here, and then combine the two maps into Ta r times Ri push forward mu. And again, we see that the push forward of nu is equal to a limit of a constant times some blowups of nu for some sequence of radii going to 0, and thus must also be a tangent measure. Now, there are other important classes of measures that also satisfy these two invariance properties, and in this video, we'll study these classes as part of a unified theory. We'll say that a class M of non-zero radon measures is a cone if it's invariant under multiplication. And we'll call a cone a decone, or dilation cone, if it's invariant under dilations around the origin, as we saw in the previous slide. So why do we call these cones? Well, the usual definition of a cone is a shape like this. So let's say we're in the plane. A cone may look like this. And in particular, notice that the points in this cone, or in this wedge, are invariant under scaling. So that is to say, if I have a point inside my cone, then so will every other multiple of this point be inside the cone. In fact, the set is completely determined just by looking at which unit vectors are in the cone. So if this is the unit ball, and this is the intersection of my unit ball with this cone, I see that every point inside my cone is just a multiple of some point on the intersection of a unit ball with this cone. And collections of measures satisfying properties A and B are analogous to these sort of Euclidean cones in the case that they're invariant under certain kinds of scaling. However, in our case, they aren't just invariant by scaling by multiples of a positive number, but also invariant under scalings of the support using dilations. And we'll come back to this analogy with Euclidean cones as a sort of visual aid later on. So let's take a look at a few examples. So first, the set of multiples of Hausdorff measure restricted to m-dimensional planes in Rn are clearly invariant under scalings and dilations. We'll give this set special notation and call it curly G and M, similar to how we denoted the Grassmannian as G and M. We could also look at a smaller subset of planes. So for example, we could look at the set of multiples of one-dimensional Hausdorff measure restricted to lines of rational angles with the x-axis. Again, this is a D-cone for the same reason that the previous example is. The set of multiples of Hausdorff measures restricted to circles centered at the origin is also a D-cone. So again, invariance by positive multiples is easy to see. And moreover, dilating length measure on a circle, or stretching its support by a factor with respect to the origin, just gives another multiple of length measure restricted to another circle. It can easily be checked that a set of M uniform measures in Rn with 0 in their supports are also D-cones, and we'll denote this set as curly U and M. Finally, as we saw previously, the set of tangent measures also forms a d-cone. Recall that the set of uniform measures is a strictly larger set than the set of Hausdorff measures restricted to planes. So that is, the cone of planar Hausdorff measures sits naturally within the cone of uniform measures. And later, it'll be useful for us to be able to measure the distance between an element of one cone to a smaller cone. So given a d-cone m, a radius r, and a radon measure mu, so that fr mu is positive and finite, we define the distance between mu and the cone of measures m as the infimum over all measures mu for which fr of mu is equal to 1 of the fr distance between this measure nu and the renormalized measure mu, so mu divided by fr of mu. So you can think of this distance as sort of measuring the angle between a measure and a cone. So again, let's look at the analogy with planar cones. So let's say we have a cone here that represents our cone m, and let's say we have a vector mu that's not in the cone. And let's suppose analogously to what we did here, so before we took mu divided by fr of mu. Let's do the sort of analogous thing and divide mu by its norm. So we get a unit vector mu divided by norm mu parallel to the vector mu. And so this lies in the set of unit vectors. Okay. So now the distance between this unit vector and the cone m is going to be a number comparable to the angle theta, let's say, between the vector mu and these cones. And the angle between mu and these cones gives a scale invariant way of measuring the distance between mu and the cone. And by scale invariant, I mean that this distance is invariant of the size of mu. So in fact, any vector parallel to the vector mu will have the same angle to the cone m. And this dr distance is doing something analogous. It's giving a distance between a measure mu and a cone m that's invariant under multiplication. So multiples of a given measure mu will all have the same dr distance to the cone m. So this distance function to a cone has a few useful properties that we'll leave as an exercise for you to verify. So let's suppose we have a radius r bigger than 0, a radon measure mu such that fr of mu is positive, and a d-cone m. Then the following hold. So first of all, the distance from mu to a cone is always at most 1. Secondly, while the dr distance function is not invariant under dilations, it does satisfy the following identity, that the dr distance from mu to a cone is equal to the d1 distance of the dilated cone mu, that is the push forward of mu under t0r to the cone m. And finally, if we have a sequence of radon measures mu I converging weakly to a measure mu, and the measure mu has fr mu positive, then the distances from the mu I to the cone m also converge to the distance from mu to m. Or in other words, these distance functions are continuous in the weak topology. We define the basis of a d-cone to be those measures mu for which f1 of mu is equal to 1. So these are analogous to the set of unit vectors in a Euclidean cone. And just like every vector in a Euclidean cone is a multiple of a unit vector in the cone, every measure in a d-cone is going to be a dilation of a measure in its basis. This means that we can deduce certain properties about the cone just by focusing on its basis. So, for example, a d-cone m has closed basis with respect to the weak topology, if and only if M is a relatively close subset of the space of non-zero radon measures. Secondly, given a d-cone M with closed basis, we have that a radon measure mu is contained in the cone if and only if the distance from mu to the cone is 0 for all radii r. So verifying these two lemmas is not too difficult, and we'll leave those for you to verify. Finally, if we see that a d-cone has compact basis, this is true if and only if there exists a constant c so that for all measures mu in our cone, the measure is doubling for all balls centered at the origin. That is to say, the measure of any ball centered at 0 of radius 2r is at most c times the measure of the ball centered at 0 of radius r. And in this case, 0 is in the support of all measures mu inside the cone. So one direction of this is not too bad to see. So suppose that we have a sequence of measures mu I inside the basis of vectors. So let's say we have a sequence mu I so that f1 of mu I is equal to 1. And we'd like to see that this has a subsequence that converges weakly to some other basis element mu. Well, notice that because the mu i's are have f1 of mu I equal to 1, okay, so recall that f1 of mu I is the same thing as the integral of 1 minus z positive part d mu I of z. And notice that this function has support only in the unit ball. Okay, so also notice that this function is going to be at least 1/2 inside the ball of radius 1/2. So this is at least 1/2 times the mu I measure of the ball of radius 1/2 b. Now, by this doubling property here, this implies that this is at most 1/2 times 2 equal to 1 times the mu I measure of the unit ball. So that's twice the ball of radius 1/2. And this will be at least 2 times the mu I measure of 2b, and so on and so forth. And this will show that for any integer k, we have that 2 to the k mu I of 2 to the k b. All of these are at most the constant 1. And so because the union of these powers of 2 to the k times the ball, unit ball, is equal to all of Euclidean space, what this implies is that the sequence of measures mu I are uniformly bounded on compact sets because they are uniformly bounded on any multiple of the unit ball. And thus, by one of the lemmas from week 1, this implies mu I is bounded on compact sets, which implies that there exists a subsequence such that mu I converges weakly to some measure mu. And moreover, notice that f1 of mu, recall that f1 is continuous with respect to the weak topology. So f1 of mu is equal to the limit of f1 of mu I, and this is equal to 1. And so thus, not only do the mu i's converge to some measure mu, that measure mu is also an element of the basis. So let's go through some examples so we get used to these definitions and results. So let's revisit the D-cone of multiples of Hausdorff measures restricted to circles centered at the origin. So this is a D-cone, but it doesn't have closed bases. So to see this, consider the sequence of measures that are just Hausdorff measures restricted to circles that are converging on the origin, so decreasing to 0, as I've defined here. Okay, and now renormalize these measures to get measures nu I. So we divide mu I by f1 of mu I. So now the resulting measures nu I are such that f1 of nu I is equal to 1. So these are all members of our basis. However, because these circles are converging on the origin, that means that any weak limit of these measures nu I is going to converge to a measure that is supported at the origin, or in other words, to a multiple of a Dirac mass at the origin. But the Dirac mass is not a member of the cone, let alone a member of the basis. And therefore, this cone does not have closed bases. Now, we could add on all multiples of the Dirac mass at the origin, and then now we would have a D-cone with closed bases. But now it will not have compact bases. And so now, to see this, we consider a different example. So instead of circles converging on the origin, we look at circles that converge to the unit circle. So I'll draw that right here. So let's say this is the unit circle, boundary of the ball radius 1, center at the origin. And then we consider a sequence of circles that are moving outwards and converging towards the unit circle, as I've defined here. And then again, we renormalize these measures by dividing by f1 of mu I. And so again, we have that f of nu I is equal to 1, and thus these nu i's are a member of our basis. So I claim that these nu i's do not have any convergent subsequence to another member of the basis. Okay? The way that we'll see this is by observing that these constants that we renormalized by are actually converging to 0. So why is that? Well, recall that f1 of a measure can actually be computed explicitly. We take the integral of 1 minus the norm of z, and then the positive part of this difference, d mu I of z. Now, observe that mu I is supported on the ball center at 0 of radius 1 minus 1 over I, which means that for any z in the support, its norm will be 1 minus 1 over I. So that means 1 minus the norm is going to equal 1 over I, d mu I of z. And now mu I is always a Hausdorff measure restricted to a circle of radius less than 1. So that means that the total mass is never going to be more than 2 pi over I, which clearly goes to 0. But this implies that the measures nu I contain no convergent subsequence. And the reason why is because the measures mu I of the unit ball are uniformly bounded below. In fact, they're always at least pi. But then if we divide by f1 of mu I, then this will imply that nu I of the unit ball will go to infinity. And so there's no way that any subsequence of nu I can possibly converge weakly to any radon measure. Now, some examples of D-cones with compact bases are the class of Hausdorff measures restricted to planes, the space of uniform measures with 0 in their supports, and the set of tangent measures of a radon measure at a point x, supposing that the measure is pointwise doubling at the point. So by one of the results from last week, this condition will imply that all tangent measures will be doubling at the origin, and the theorem from the previous slide will imply the D-cone of tangent measures has compact bases.